Well, now we've got the presentation you've been waiting for. By the way, I should add that one of the things you've not heard this morning, as each speaker spoke, saying, I wish to assure you that what I have to say is purely my own view and is not attributable to anyone in mankind, probably their spouses also. I must say that with regard to Ed Key. He comes from Rockwell, but I can assure you that Rockwell does not consider itself a party to his presentation. He is going to talk about a low-cost space transportation system. And so he may have the answers for us as to how we get there from here. Please, Ed.
Thank you. Can I have the next slide, please? This is actually the second of a series of 3 presentations. The first presentation, which was the opening one, stated that after we looked at all the aspects of a rocket, I determined that you could build one commercially that could take cargo to space at only $22 a pound. A very revolutionary idea, and one that there's a lot of resistance to, even if you can prove it to be true. And we're going to talk about economic impact and applications at this particular conference. And a month from now in Sacramento, I'll be discussing how you can turn this theory at $22 a pound into a reality. What sort of processes have to be done to make it work. Next slide, please. Right now, here's what we have currently. We have 3 great American rockets, and as you can see, they're very expensive, and they're very, very good rockets. But they all have something in common. They're all approximately $5,300 per pound that you take up to space, and they're all meant for one particular class of cargo. That's cargo that is very valuable on Earth or in space. And we're looking for something else, some other market niche, something you can take up things that are cheap on Earth and expensive in space. For example, propellant, the TV dinners these astronauts will use, and the supplies and cargo they'll need at the space station. Especially considering that any manned space endeavor is very mass intensive. We can shrink and we can miniaturize all these electronic and sensor functions. We cannot shrink or miniaturize people to any great extent. We also should look at the bottom here is our competitors on the other side of the next continent over. And they have a very interesting space infrastructure, which they claim they can get cargo to space with current vehicles for anywhere from $780 a pound down to $272 a pound. Interestingly, the low targets we have set previously for the ALS system, which is now virtually defunct, and it said that those cost figures were too optimistic. And what we're looking at is shrinking it out even more. I believe personally, after having looked at these Russian rockets, that an American manufacturing company could build them with as good quality as the Soviets do, and actually build them at a lower cost than they can. And if we take that, why can't we build especially a rocket that takes all the advantage of the technology and the industrial processes we have in America and bring the costs even lower? Next slide, please. This is just maybe not show up too well here, but that's the tail end of the Russian SL-4 rocket. It goes against many of our American manufacturing beliefs. For example, we want to always build as few engines as possible, make them largest. That's the economies of scale. The Soviets, this thing lifts off with 32 engines blazing. And that's really economies of scale. Think of it. They're in mass production when they send one of these things up. There's not a single American large rocket engine that enjoys a production rate of even 12 per year at this time, and hasn't for a long time. Next slide, please. So by the way, we means myself, but I have a lot of friends out there. It doesn't mean Rockwell. We have set a cost target for these, which is very stringent. We're looking to set 15,000 pound payload, which is the scale we eventually decided was optimum for this sort of market, for only about $250,000. And these figures are from a cost model, but we believe that that the design is specially made will fit all these costs. And imagine what that can do to space. Next slide, please. And just a little validation from the previous paper, and I do have copies of the previous paper available for those who are engineers and would like to look this over and say it's too good to be true. Our presumptions we used in all the cost models were a vehicle that would require 30,000 feet per second of ideal velocity to get to orbit, a reasonable assumption. A specific impulse on average of 250 for the first stage operation, 300 for the second, third, and fourth stage operation. Some people may think that's a little optimistic, but we have methods of making that work. A propellant pad, just assumption that 0.6% of the propellant you have will not be usable. And an expectation that we can build this thing as a clustered rocket architecture that only carries 11 pounds of propellant for every pound of rocket machinery. Next slide, please. And so this is the scale we came up with. We feel that our rocket would weigh almost 30 tons dry, a very heavy rocket. Weigh 700,000 pounds of gross liftoff weight, which is also very, very heavy, for a rocket that can carry a payload of 15,000 pounds. It will be made up of a cluster of 7 identical rockets, by the way, so you are already well on the way to mass production even with a single vehicle, and also you're only developing something that's 1/7 of the scale of this. You're only building basically rockets that are 100,000 pound gross liftoff weight class, but they are strapped together. Next slide, please. Now we're getting to the economics part. And we're going to go ahead and state the problem and also give my disclaimer to Rockwell International, because this is perhaps the area that we had the greatest concern. They didn't like the idea that there was some negative statements in my paper, and I apologize for saying these statements. However, that was very mild compared to what I've heard at this conference. And I'm going to say the statement of the problem is that getting cargo to space is such an expensive undertaking that the American space program is grinding to a halt. And I don't know, does the audience agree or disagree with that? Yeah. Okay. Next slide then, please. And I'll purge all my negative slides except for this one. This is the American launch rate that we have on a yearly basis. And I just have a hard time seeing the American launch industry as a growth industry with this sort of a record. And I would like to be able to turn it around. One more slide in comparisons to our greatest competitor. This is a comparison of the entire American launch rate in the light gray, and you can see, I'll bring it down a little bit. Okay. As you can see on the left side is the total American, no, on the right side is the total American launch rate, which is the dark. And on the right side is not the Soviet launch rate, that's the launch rate of a single vehicle, the SL-4. And what I found amazing is you look at during the decade of the 1980s and the 1970s, how close and consistent they are. They have been launching one rocket per week on average for more than 20 years. An amazing feat. We couldn't afford to put that many payloads above. So we can go on into the next slide, which is onto the economic impact. And I'd like to talk about some historical breakthroughs that have occurred that have scared people to death when they first came down and turned out to be breakthroughs that have changed history. The question, did the invention of the cotton gin, which made cotton from a very labor-intensive to a less labor-intensive effort, did it ruin the cotton industry? Did the PC destroy the computer industry? That's another great step forward.
You're right, yeah.
Skipping over the machine gun, eliminating massed armies, we know that hasn't happened. Did the invention of the sewing machine, which allowed one tailor to do the work of 40 tailors without sewing machines, did it destroy the garment industry? And now, in the same context, will low-cost space transportation destroy the American space industry? Unfortunately, I think a lot of people think it would, and I think it would not. Let's go look at the breakthrough effects. The cotton gin made cotton so profitable that even though the price did drop, as people feared, cotton became king. There were some unfortunate historical things that did occur that perhaps could be said that it led to the American Civil War. But as far as an economic success, it was outstanding. The PC revolution, I don't even think I need to talk about that. Everybody knows that PCs, which used to be, or computers which used to be devices for major institutions, now reside on the desk of many ordinary people like us at home. And the sewing machine, yes, it did cut the cost of garments. Garments went way down, but it didn't put any tailors out of business. It, in fact, encouraged a brand new garment industry based on factories. More tailors were needed. And where previously people had only the clothes they wore, after the sewing machine, people started having wardrobes. A new market that didn't exist at the time of the sewing, before the sewing machine came along, now came to be. Next slide. So what I'd like to emphasize is that low-cost space transportation is not a threat to Rockwell or General Dynamics. It's not a threat to Boeing or McDonnell Douglas or Martin Marietta, people who currently have space transportation systems right now. And in fact, what I'll try to show is that it will not displace these markets at all. Those markets will still exist just as healthy as today, but like coach seats in airliners, will represent a new market that will supplement rather than displace the existing markets. And it won't make current technology obsolete. In fact, what I'm proposing is a rocket that takes advantage of the technologies we already have. Nothing in the rocket design I'm proposing uses any technology that does not already exist and does not even take advantage of any rocket methods that haven't already flown on one rocket or another. And also, since we're talking about saving money, this scares a lot of people these days. They are afraid that if we talk about saving money, there'll be cost cutting. Cost cutting means lost jobs. I maintain that this is not true. That if we're able to bring down the cost of space as far as a per project basis, we will be able to afford a lot more projects, and the number of greater projects we have will overcome any savings on any one individual project. Next slide. In fact, program killers are, and I want to make this one very clear, when I'm referring to fireballs east of Cape Kennedy, that's not the Challenger. That has to do with the way things were done in the 1950s, where programs indeed were destroyed by launch failures or failures of new systems. The debris was the death knell of those particular programs. No, instead, programs die because they expand the cost. The cost continues to spiral outward without really adding additional benefit from the program. And this not only kills the program themselves, it also takes valuable funding like a sponge away from other worthwhile programs and raises the threshold of what it is that we can now look for in space. In fact, unfortunately, it's come to the point where we can no longer have a serendipity type space program. We can only go into space looking for things that we already know exist. We can't search for things that may or may not be there. Now, on to economics. We try to decide if we can get something to orbit at $22 a pound, what kind of a market we'll have. Here's one possibility. It's an elastic demand curve. It says if the cost of launch services goes down, the payloads will also go down equally with it. That can be realistic for some programs, but that wouldn't happen across the board. So we can go to the next slide. Another extreme is what happens if the cost of launch services go down, but the payloads stay at the same price. Then there won't be very many more programs either. So what we came to with the next slide in my research was that, by and large, a lot of the programs, including, we're talking about government NASA type programs, should, however, vary with the square root of launch costs. And the particular author on this paper that I referred to, his conclusion was that launch costs were not a bottleneck, because as the cost of launches goes down, the cost of the payloads and the whole overall mission only goes down by the square root of it. Not very significant to him. But however, if we're talking about a drop in launch costs for many kinds of materials of a factor of 200 to 250, then there's significant savings on major programs. For example, on the next slide, I can very well envision $100 million satellites dropping down to about $7 million each. Of course, there'd be a lot more of them too. After all, the Russians use exactly that as a strategy. They put a lot more satellites. In fact, that's the basic difference between the American space program and the Russian space program. We are an engineering-oriented spacefaring nation. The Russians are a manufacturing-oriented spacefaring nation. I can envision $1.5 billion Galileo-class satellites, a lot more of them now, being reduced to about $106 million each for the whole program. Can you imagine how many extra worlds we can explore with something like that? $37 billion space station. If we were to start over from scratch with some of these presumptions, perhaps it might be $2.6 billion. Or even once the space station is up there, can you imagine how much it could relieve the space shuttle as a supply vehicle using probably our greatest vehicle to carry TV dinners up? I think that we could probably find a better use of the space shuttle if we had the supplies offloaded from the space shuttle and moved on to one of these. It would allow the space shuttle to do dual-purpose missions when it goes to the space station, drop off a high-value cargo in orbit, and continue on the space station for the second part of the mission of changing out crews.
Just a few more minutes.
Yes, okay. Next slide. This is the conclusion on the economic side. I'd like to skip that over that and just go to the two vehicles I think could go on top of this. One thing, if we build such a vehicle, I don't think we'll have a bunch of customers walking up and say, yes, we want to get on top of your vehicle. You're going to have to put another product on there as the ultimate spacecraft that people can use. And these two products I came up with is a modular universal cargo carrier, which you'll see on the next page. Actually, this is not original. This is what the Russians do on their Soyuz. And as we go to the next page, I'll show you a Soyuz. You've probably all seen it. Looks like a high school attempt to build a welding class attempt to build a diving bell. It's not very pretty, but as you look at it, it's a very important spacecraft because, as you see it here, it carries people, and it's called a Soyuz. Very similar to this, it's a Progress, and it carries supplies to the space station. If you put a monkey into it, a monkey chair, it's a biosat. If you put material processing in it, it's a MatSat. If you put cameras in it, it's an imaging reconnaissance satellite. And in fact, the Russians pretty much use this spacecraft in its various forms as every single payload on top of an SL-4. And I have the expert over here. Okay, so if we go to the next slide, we're looking at bringing down the cost also of these modules. Well, I have on my first paper as to how we bring the cost down. We're saying that we have to bring down the cost of building machines for rockets down to approximately the cost of automobiles by making it simpler and so forth. And that's about $3 a pound. And so I'm saying that we should be able to take spacecraft, which are made of aluminum and high-class electronics, and bring the cost of those down to about $50 per pound, which, if you believe the first premise, you have to believe the second. If you don't the first, the second doesn't matter. So if we can skip over several slides, I'd like to go on to just the applications. And I'd really like the audience to think about this one. I've only come up with a few scientific research. If you put the Soviets, if they have something new to test, they don't test it in laboratory. They'll put it on a Soyuz and let it be a free flyer. They test things in space. They would know if an antenna could unfurl or not. They would know a lot of things that we don't because we don't test in space. Space research is limited by money. If the cost is down, there will be a lot more research. I'm not referring to multi-million-dollar satellites, but what about satellites in which researchers can take off-the-shelf equipment and plug it into a carrier satellite, which provides all the service you want, your delta V and your attitude control, your communications, your power, and perform their experiments in space at under $500,000. biology experiments, so we don't have to experiment with monkeys, not humans, and so forth. Propellant delivery, critical for the space exploration initiative. And space station supplies would be also well, and we could even supply extra supplies to the space shuttle, allowing it for about $750,000 to extend itself in orbit for another week without lowering down the amount of payload it could carry. And then the second product I'd like to talk about would be propulsion. Maybe I could have used a better choice of words, but they call this particular item a pusher, which is just a propulsive device that can attach that can meet any other spacecraft in orbit and push it to a higher orbit. 3/4 of everything we've ever put into space has been propellant or upper stage propulsion. And this is a huge market. Imagine if you don't have to fill the entire payload bay of a space shuttle with a Galileo, but you could put half a dozen or more of them in and meet the propulsion in space if the propulsion was cheap enough and dependable enough. Next slide. And again, I'm not looking about anything new. This pusher model is merely taking the specifications of the Delta upper stage made by Aerojet, a former employer of myself, and just postulating that it would use something like that as a expendable rocket, which, as the next slide shows, would be disposable with a little bit of residual propellant into the ocean after it raises whatever it has to a higher staging orbit. Next slide. And I think this is something that we prove out a lot of NASA's concepts of space tug operation with this particular sort of propulsion. It would act like a space tug, but would be much cheaper, and it would allow them to learn all these operations in space rather than sit around in conferences deciding how they think it will work. Next slide. And there's the bottom line cost of what I feel one of these propulsion units would cost. Under $500,000 delivered FOB in orbit. Next slide. And so what we'd do is we'd use this in order to, let's go to the next slide. I've already covered that. I'd like to show you a sample, just to get back to the practical aspect. If you had these pushers and you wanted to support some sort of a lunar system. And on all these, I presume that you have a final lunar carriage or something that gives you that last 1,000 feet per second of delta V for your soft landing. It would take, on average, one of these pushers at under $500,000 to deliver a ton too close to the lunar surface, to within 1,000 feet per second of the lunar surface. It would take 14 to 17 of these pushers ganging together like a train, pushing one after the other and dropping off, and you could drop a 15-ton object on the surface of the moon. There's nothing magical or high-tech about this. It's a very brute force method, but it can be done. And let's go on to, from the moon, which is familiar, to something a long ways away, an asteroid rendezvous mission. There's not a rendezvous, but a soft landing on it. And what would it take in theory? For such a system would take approximately 8 pushers to get you there, way out beyond Mars, and another pusher to make a soft landing on such a planet. Such a vehicle would have a total mass in orbit of about 131,000 pounds, too big for anything today. We can't even comprehend that. But with the addition of these very low-cost propulsion units, we can take some of these Mariner Mark II satellites that NASA wants to send to Saturn and for asteroid rendezvous and flybys, and we can permit them to make large numbers of them and still get them in there at very low cost. Finally, in summary, just talk about the economic impact on space transportation is that I think the impact would be positive, not negative. It won't cost jobs. It will open up the space industry. It's an area that we really need to look at, and it's the only area that we lag behind the Soviet Union on, and that's transportation from the surface of the Earth to low Earth orbit. It would make space station and manned Mars missions very affordable. And in fact, I believe that with systems like this, it would change the arguments we had at this conference. Would no longer be talking about should we go to the moon or to Mars, or should we really have a space station? It would say, yes, we can have a space station, a lunar colony, and a Mars mission concurrent, sooner not later, and all in a much shorter period of time than we're currently envisioning, and at a lower cost, and at less burden to the taxpayers. Thank you very much.
Questions from our speakers? You got
Yes.
money for this yet?
This is only the second conference I've been to. I
Okay.
picked this up in February. I would like, though, however, like serious investors to come up to the center and NASA to come to the right. And just the curious over here. Any other questions?
Yeah, the ALS program was an attempt supposedly to start with a clean sheet of paper and using cost as the main criterion, try to design a low-cost, versatile, multiple payload type launch system. How come they came up with very different answers than you did?
Well, actually, I came up with the same answers that ALS did. If I had the same constraints, it wasn't really a clean sheet. It specified liquid hydrogen, liquid oxygen engines. It specified a size that was going to be so great that you wouldn't have the high launch rates. Giving you a little example as to what I'll be saying in the Sacramento conference is this thing is scaled so they can virtually have a launch every day from a place like Spaceport, Hawaii at these sort of costs. And you couldn't do that if you had a giant vehicle that required so much integration of payloads. A close attention to what sort of payload you'll have is critically important. There was a lot of things that were not clean sheet on the ALS, and in fact, within the aerospace industry and way of doing things, I think that ALS was a possibility to bring the cost down to $300 a pound. That what I'm looking at is the things to bring it down from $300 a pound down below that to $22 a pound.
By the way, your costs seem to be just direct costs, really manufacturing launch operations. What kind of overhead assumptions and what kind of cost of capital, et cetera?
And launch operations.
Yeah.
Yes, that's the benchmark price that's ordinarily quoted. I think the most important cost to look at is how much will it cost to develop such a system. If in a commercial environment, it wouldn't be very much. In the aerospace environment, it would probably be about $250 million, $250 million approximately. Remembering, of course, that part of the way we designed this was so that we could have a design that's really a small rocket clustered together to make a big rocket's ability. There's a lot of reuse of design in the way we laid this out, and part of the cost target was to make it so it was not only cheap once you get it in operation, but also cheap to build in the first place, to develop and design.
We'll take one more question. First, before we do, some of you are interested in the Soviet program. Tomorrow morning, I'll have a session for about 45 minutes, and we'll kick that all around. But one thing you might not realize is that when the U.S. assigns a cost to a Soviet program or a Soviet capability, the way that our people, CIA and what have you, cost that out is by asking the question, what would that cost to build in the United States with U.S. engineers? So that's the cost value, and it's not entirely inappropriate, but you just ought to know that's how they arrive at a cost for something to occur in the Soviet Union. And I have one more question. Yes, sir.
I'm going to ask this a flip way first and a serious way second. Are you afraid of being assassinated?
Not until people start taking this seriously.
I guess that's my point. I can't help but feel that the companies that have a large current investment in doing things the way they've always been done are going to do everything they can to suppress this. I don't guess that I can ask you to directly agree or disagree with that statement, but the question I have is, how do you expect to translate this into reality? It has to be not through a conventional means. I just can't see any way that any of the big companies are going to take you seriously.
Well, that's where you have to show them that this will not erode their current markets. That there will be an expanded market for the high-value satellites that they launch, supplemented with propulsion that we can supply. That there will be more of a market for what they already have than there is now. And that's the main point. As we bring costs down, and this is only one component of costs, but it helps bring the average cost of all programs down, then, as markets do, there will be greater total revenue available for all these companies. And I don't think it's going to erode the mission of the space shuttle at all, for certain, and not likely will it erode a need for things like Atlases and Titans and Deltas?
You know, the thing is, you're making completely good sense, but remember, the railroads do not see the value of trucking, okay? The wagon manufacturers saw no value in cars, except for Fisher Body, and that was absorbed. You know, each generation somehow is unable, in general, to understand that their purpose in life is not, you know, building a certain widget, but in the larger picture of transportation. And so these people are going to have the same problem in general, you know, that they cannot see that transportation is what they're in the business of and not big rockets. And so they're going to see you as a competitor they cannot allow to continue. So you have to start your own firm and make your own millions. And then as you grow old, there'll be something else going on the pipe, and you'll be having your own troubles understanding.
Let's give him a hand.
If that was the question, part of my answer is I do believe that some of the large companies can be shown that this can be profitable. A large company that would go ahead and accept these would probably at least have a good chance of becoming the IBM of space. And if they understand that, if they don't feel threatened, and that's the hard part to get across, it's a lot easier for me to convince them that you can get to orbit at $22 a pound. That's an engineering problem, and I can show solutions, than it is to show them that their markets are still secure and that they will profit by this and that they will be better off for having it rather than worse off.
Thank you.